Okay, real quick, homework on the board. That was the stuff I gave you yesterday. I put it over there so you can see it. Just make sure that you are working on that. I will give you time today to work, actually quite a bit of time. I'm going to go through a couple things really fast because I said I want to give you some time today to work on that because it is due Monday. So keep that in mind. On those radicals, try to break them down to simplest form. Now there's one problem we didn't cover yesterday, and I want to make sure that you actually see an example of it. This is the one problem I said yesterday when you're actually right before I went to the where I said I'm not going to cover it. I want to see how well you can do. It was a problem like this. It's like in the middle. It was, I don't know, 39, somewhere in that range. Okay, something like that. This problem is a rational problem, right? It's got a fraction, but it has a radical on the bottom, so you have to get rid of it. The problem is you can't just multiply by radical 7, other than all those examples I did the other day, because it has a plus sign. This is actually a binomial on the bottom. So if you multiply by a radical 7, it would have to distribute over the bottom, so you'd still have a radical 7 there. So the trick is, on this problem, is to multiply by a conjugate. And this is a term that I was hoping that you know, but I better cover it. So conjugate is any time you take a binomial and you basically write not really the opposite of it, because an opposite is changing all the signs. It's just flipping the middle sign. So the conjugate of 2 plus root 7 is 2 minus root 7. That is not a perfect opposite. Opposite would make the 2 negative as well. But this is what you're going to choose to multiply by. Now the reason why this works is because of the stuff we're doing today. And that's why I kind of waited. The stuff we're doing today is talking about binomials and trinomials and how to multiply them. It will basically explain when you multiply by that conjugate why the radicals drop out. Okay, but I'm going to do the math so you can see this. So I'm going to multiply by a 2 minus root 7 and 2 minus root 7. Because remember, whatever you do to the bottom, you have to do to the top. The top, I really don't care about. It's really just getting rid of the radical off the bottom. So we're rationalizing still. So on the top, you have to distribute the 5 to everything. So we're going to get 10 minus 5 radical 2. Notice I didn't actually multiply the 5 into the radical because it's not in the radical itself. So you just put it out front. So that's the top. Do we feel comfortable with the distributing of the top?
Yeah, I don't know how 7 turned into a 2.
What?
How did 7 turn into a 2?
No idea. I think so. There. I don't know how it turned into a 2, just go with it. Alright, bottom. We're going to multiply it. We're going to FOIL, first, after, and last. I just think it was distributing twice. That's all I do. So you're going to take the 2 times everything and then take the 7 times everything. It's distributing twice. 2 times 2. 2 times negative radical 7, so that's negative 2 radical 7. So that's the front one. Now the back, radical 7 times these, that's plus 2 radical 7. And then a positive times a negative is negative, and radical 7 times radical 7 is radical 49. Now I know that a lot of you can simplify that to the number 7 itself, but I want to show you why this is going to work out. When you actually distribute, or you multiply, or FOIL, however you want to say it, the reason why you choose to multiply by a conjugate is sitting right here in front of you. That what happens when you do this and you pick a perfect conjugate, it cancels out the middle terms. One's positive, one's negative. That's the reason why we choose just to make the middle number negative when you're picking your conjugate. Because it'll make the middle numbers the exact same, but opposite signs. And then the outside terms will be perfect squares. So you're seeing it. 49 is a perfect square. The 4 is a perfect square. So those are able to be, those problems are able to take a square root of them if you have 2 radicals. So on this problem, the radical 2's, the radical 7's cancel out there, and then this 49 in the back just turns out to be 7. So it's 4 minus 7, or 4 minus 7 on the bottom. And the top didn't really even change. Questions with the concepts of what you have to do in that problem? I think we only had one of them. I just didn't explain it yesterday because it fits with what we're doing today. So I kind of wanted to wait on it. Questions at all? I don't know if you've ever seen that before. Maybe you have. I don't know. But it's nice to see at least once for me, so you kind of remember it. We're going to talk about that today. We'll come back to it. You don't go last month, but I think it's in the middle. I think it's like 39-ish or 33. It's one of those. One.
It's 50.
50. There it is. It's in the middle. Okay. All right. Moving on. Let's go to polynomials. We have to go through the definition of a polynomial, and then we'll get to the stuff and why we're doing this. Okay. All right. Here we go. Let me put it up on the board. This is something I'd like you to write down. Take a picture of it right out of your textbook because you need to see the actual definition. Long and complicated, you need to write that. As you're writing it, I'll kind of read it out loud. Okay, definition of a polynomial in X. I don't know why they always say that. It's in X, it's of X, it's using that variable. Polynomial in X is an algebraic expression, so it's going to have numbers and letters combined with basic operations. But it's got this weird form, and the form is the thing I want you to write down, and that's the part I want you to focus on. It's this monstrosity here that they've written for you. There's a to the sub n, x to the exponent of n, and then n minus 1, and they keep going down. There's a dot in the middle because there's a pattern. You know, it's a series kind of a thing. And then where the a to the n, a to the n minus 1, a to the n minus 2, all those are real numbers. Those are digits. Where a to the n cannot be 0. N is a non-negative. Bless you. So those are non-negative numbers, no matter what, even in the sub, the sub numbers or the subscript or superscript. I'll explain that. It's degree n. We'll talk about what degree is. It's got leading coefficients. It's got a constant. There's a lot of vocabulary, but this definition is directly out of the book, and you need to see it. Sad part is, polynomials are something you probably dealt with since Algebra 1 or pre-algebra days. You probably have seen a polynomial, but the definition has really never been taught properly. They just teach you, basic operations, and they just go from there. They don't actually ever start with the definition. So no one ever really gets the full picture of what it is, what it means, what it should look like. There's little rules to it. I'll show you some of the rules you need to think about. Once you have this down, then we'll do a couple of examples of it today. So if you're done with the definition, I have an example on the board of a polynomial. And we're going to talk about, the naming of it, the degree of it, that type of thing. And these are just little things we need to think about, and I'll try to explain how the definition directly applies to this thing. So it looks more complicated than it really is. But there's a reason why it's so specific, that there has to be, a of n cannot be 0, and you can't have negative numbers. And I have a certain degree, and it's got a leading coefficient as a constant. Every term has to follow. I have to follow those rules really strictly. So what you're looking at here, this is a function, right? It's a polynomial, it's going to be a function, algebraic expression, that type of thing. This part right here, this is the name of the actual function. This is the actual variable it's using. So that's the part they're trying to explain in the very beginning. It's a polynomial in x or of x. That's the variable they're using. That comes from the name. The equal sign is just say this is the name, this is the formula. So it's not really an equation. It's just saying that this is the name of it and here's your formula for it. Now, the rules. They have leading coefficients. Okay, the numbers out front of variables. The back term, this term is called the constant. That is your a to the 0 term. In fact, let me write that above. This is a to the 0 term. A sub 0. Okay, a sub 0, or subscript of 0, is the constant. It's the last, it's number 0. It's the absolute last number, digit, leading coefficient number in the polynomial written. So as you go up, there is a of 1, and then there's a of 2, and there's a of 3. Now, certain ones can be missing. You could be missing, I don't have to have an x term. You can have polynomials that look like this. Like that, where I'm missing the x term in the middle. But you can fill it in. You can figure out what number has to be sitting there. The number's in front of your variable. Now, why they number them? They go up in order, right? They start with the first term, which is a of naught. That's they always use a naught or a of 0 for anything that's initial, the starting number in a sequence, or the initial amount of bacterial in a jar, right? That's your initial amount, so it's a of 0. Time of 0, this is how much we have. And as it grows up, there's a time scale to it. Well, that's what they're doing here. They're counting up. Every time they count up, the variable will go up by the same power. So x of 1, or in this case, there's a 2 here, so that's x of 2. And you're seeing them. And then at the very end, same thing here. They have x of 0. But what is x of 0? 1, right? That was the law of exponent. Anything to the power of 0 is 1. So they just don't write it. So if you look at the definition, you can see that. In the very end, there's no variable on it, because it's x of 0. Now they happen to be using n's and x's. That's a little weird. That's a misprint. I just meant that as a misprint. It should be an x. Make sure that's an x, not an n. If you wrote an n there, it's a misprint. That doesn't happen very often. I have to submit that. Okay, but it's got degree n. So what degree n is, it's the last numbers. So if you go through all the polynomial and you're looking at the last or I guess in your case, the first variable, if you put them in order, the first variable, this is the degree. So this is a degree 2 polynomial. So the highest degree is 2, the highest power, the highest exponent. Why that's important? Degrees on that tell you how many potential roots there are to this problem. What I mean by roots, because polynomial equations, they have radicals usually for answers, but a root is at any time it crosses the x-axis. So in theory, this thing could hit the x-axis twice. And that's something we're going to learn throughout this year. Graphing polynomials, graphing quadratics, hyperbolas, parabolas, that type of thing. We need to be able to draw it, but then we have to use these basic concepts, this definition. This is an important number. In theory, I will hit the x-axis twice. There's 2 x-intercepts. Some people just don't think about that. That's important. That's why we do it. The power of n up here, the first power, like the biggest power of your polynomial, however big it is. They start with x1, x2, x3, whatever one you end at. That's your nth term. So in my case, my nth term is the second term. Okay? It cannot be a 0. If this is a 0, you're back down here, and you don't have a variable. It's just a constant. To be a polynomial, we have to have at least one more term past a of 0. You have to have at least a variable. Otherwise, if you don't have a variable, it says it in the definition. If there's no variable, you have a constant, a of 0. So they have to be non-zero terms. So a of 0 is real, the numbers a of n and n is a non-negative integer. Like, you have to think about that you cannot have 0 in the very front. So the idea is that right here, there should be a non-negative. You cannot have that first term being 0. Why would you have the first a of n being 0? There should be a slash through that, by the way. There's a second typo in there. Okay, so you got to have non-negative numbers. So the idea is that these powers cannot be negatives, because if they're negatives, they're on the bottom of a fraction, right? So if you had a power like x to the negative 2 with let's go 6 up front, this is what you're going to have. The x is on the bottom, right? Because x has a negative power. That's not a polynomial. Polynomials don't have division. It's all multiplying or adding and subtracting. That's it. You're seeing it right there. This can be an expression. It's just not a polynomial. So keep that in mind. All right. Questions, comments, concerns about the definition? A couple typos there. I'm not happy with that. Okay, good. So, next then, let's talk about some basic operations. What we're going to learn on Monday, what we're going to really focus on is the basic stuff. Adding, subtracting, multiplying. That's what we're doing, right? So, let me give you an example. 4x squared plus 9x. Or add x squared minus 3x plus 1. Okay, adding polynomials. Wow, you guys have probably done that since Algebra 1 days, pre-algebra days. Great, fine dandy. How do you do it? How do you add? What do you think? What's the rule?
You add like terms.
Add like terms. That's a perfect way to put it. And you add like terms. You add only the things that have the matching variables. You don't actually need the parentheses. They're just there to mess with you. So I would be adding the 4x squared and the 1x squared. Yes, there's a leading number up front of 1. I would add the 9x and the negative 3x and the 1 in the back. You don't actually need the parentheses. You group, you add, that's your answer. The degree of this thing will be degree 2. It's got the highest degree of 2, as long as those variables stay around. Okay, questions on the first type that we're going to really focus on Monday. Now I know this is simple and stupid, but what happens if I were to throw a negative back here? So we subtract the 2. Now what?
You subtract it.
Yeah, how?
Take. No, I got it.
Yeah, you got it.
So take 4x squared minus x squared.
Okay.
And take 9x plus 3x.
Okay.
And then you have it minus 1.
Okay, let's talk about that. Why?
Or you could just change all the signs like you did right there.
Okay. Okay, but why did you get the negative 1x squared? Why did you get the positive 3? Why did you get the negative 1 in the back?
You distribute
Easier.
the negative.
There's what I'm looking for. You distribute the negative. Yeah, you're absolutely right. You're right. What you said. Okay, you're doing the right terms, or you're subtracting your ends. But the big thing is you're distributing the negative through the back. Now, here's the part you need to be careful of. If you distribute the negative in the back, and you do this idea where you have, the negative x squared plus 3x and then negative 1, right? You distribute the negative sign, and you have that 4x squared plus 9x here. You're not multiplying. You're still adding and subtracting. I don't care that the negative went through the back. Once you distribute the negative through the back, the parentheses are gone. They disappear. You did the math that you needed to. You would not believe how many people in previous years distribute the negative sign and then they try to multiply everything together. You went way too difficult. They're subtracting. The overall property here is you are subtracting things. Don't multiply. Okay, questions on the first part? All right, last problem of the day. This is my absolute last problem. And then I'm going to give you time to work. Okay, it's polynomial, got a degree on it. What do we need to do here? What is this problem asking you to do? what does that little 4 mean?
Everything to the left.
Okay, so you're saying that I could do this?
No, I gotta get 4 binomials.
Ah. 4 binomials. Your power 4, you're correct, but you have 4 of these. Because the definition of an exponent says that whatever your base is, you have that many of them. Now, how do we do that? Yes.
You foil 2 of them and then foil that with the next one, and
Yep.
then foil that with the next one.
Yeah.
Oh boy.
You foil 1 at a time as you go through. Okay? So we have to foil these together. That's going to be 9x squared plus, let's see, 6 and 6 is 12x's plus 4. Then we're going to have to foil that to the back term. So I'm doing 2 parentheses at the same time. So now you're taking this times the next one. Or you can multiply these in the back together. You go count it any order you want. I'll multiply the ones in the back. Now, I multiplied, now I'm going to multiply those last 2. How many items should I have across the board?
4. No.
It's gonna be 6, but then you can combine.
No, there should be.
It'll actually be 9. It'll be 9 items, and then we'll combine down.
Oh, so you're
because-
talking about, before the fact.
Yeah, because there's 3 items in here, right?
Right.
There's 3 items in here. You'll have 9 items. 3 times 3 is 9. And then we'll combine and maybe we'll get down to 6 or we'll get down to 4 or whatever it's going to be. We'll be able to simplify at some point. The reason why I know we'll be able to simplify, they have the same numbers and letters in there. They don't have any other weird variables. There's just X's and numbers. So we should be able to simplify, not very far, but you should be able to. Now, do you agree that that process is tedious? Long. It is. Especially when you have a problem in your book that has power 8 on it. Whoa. Okay? Or there's a problem with power 12. Okay? If I had to do power 12, it would take me more markers board space than I have room in this room. And I have 4 marker boards in here. And I wouldn't be able to probably finish it for a while. There's a shortcut for doing things. And I don't know if you've ever learned it before. There's a shortcut that will get you to your final answer really quickly. But the process is tedious. Like it requires that you have a chart that's in front of you, and then you have to follow the chart super meticulously, like strict, okay? We're gonna practice that Monday. I don't have enough time today. I want to get back to work. Just be ready to go Monday. We're gonna do these types of problems, but I'm gonna put really big powers on them. Like where you won't want to do anything, okay? All right, the rest of the time, you have time to work on your page 43. It's due Monday. There you go.
Can't wait.
I need to fix that. I don't know why. I need to either submit that or fix it. Not having that.
Maybe you should have breakfast.
Oh, yeah.
Did you hear that?